Let's begin. As you know, we have been doing hypothesis testing, and that's very fundamental to all of machine learning. Okay, the reason is that in machine learning, our main goal is to predict and generalize based on a small sample from the conceptual space. So if a computer vision system is uh, is trying to do a distinction between dog and cat, for example, so lots of dog and cat examples will be shown to the vision model, and in future, any unseen dog or cat image will be branded, will be labeled appropriately. So in this, of course, we have this important notion of accuracy measure. So let's say the accuracy is 80%, 80% on the test data, which is a gold standard data. So let's say we do this testing and find out the accuracy of 80% on a sample from the conceptual space of dog and cat. And then we would like to take a leap of generalization and say that in the whole conceptual space, my accuracy will be 80%. Okay. So this is a leap of generalization, and we would like to have confidence in this claim, right? So based on 100 test data, I've seen an accuracy of 80%. And now I'd like to claim this 80% accuracy for the whole population space. Okay, so I should give a level of confidence for this. So these are the concerns which are there in hypothesis testing, and this relates to the problem generalization from the small sample that is seen by us. So this is really very fundamental to whole of machine learning, and we are spending some time on hypothesis testing for this. So today I decided to show you the nitty-gritties of hypothesis testing with the simplest possible example. Okay, the example that we always see, which is in the form of head and tail when a coin is tossed. Okay, so this example is used in whole of probability, statistics, machine learning, and this is used to illustrate techniques which are generalizable. Okay, so through a very simple example of coin testing, we would like to illustrate the principles and the procedure of hypothesis testing. Okay, so let's go to this example first. Okay, so the setting is as follows. A coin is tossed 100 times, and there are 70 heads. Okay, this we are doing on the board. And the question is, do you think the question is biased or unbiased? Now, the intuition in our mind is that the coin is biased. Okay, and that's because we have got a large number of heads. 70 outcomes out of 100 are heads. So we would like to believe that the coin is not biased. Now, if you remember the methodology of hypothesis testing, the first step is H0. Okay, we fix what is called a null hypothesis. Now, we would like to assume that the coin is unbiased. So if the coin is unbiased, then the probability of obtaining head is 0.5. And that would mean the value of the number of heads should be close to 50. Okay, so that will give us confidence that the coin is unbiased. But since we have got 70 heads out of 100, we would like to prove, okay, that this coin is biased. And in this case, we would like to contradict the null hypothesis. So notice how we are setting up the stage of hypothesis testing. We are starting with the statement that the coin is unbiased, and that we would like to contradict because of the data. So the data that you have got in front of us is 70 heads out of 100. Okay, and we know that the coin cannot be unbiased, but we have the null hypothesis that coin is unbiased. Therefore, the probability is 0.5. So that's an assumption. Okay, the null hypothesis is always an assumption, and we would like to show that if the null hypothesis is true, then the data cannot be true. But the data cannot be false. Okay, data has to be true because data has appeared. Therefore, we'll have to nullify the null hypothesis. So obviously, the null hypothesis is false. How do we show this? Now, very carefully mark the methodology of hypothesis testing. Even if you've done this before, doesn't matter. This is a very very nice way of clearing the concepts of null hypothesis. Now, so the first step has been taken. The coin we are saying is unbiased. The next thing we need is what is called the normal approximation. Okay, I'm sort of jumping the gun a bit because we would like to make use of the normal distribution. For hypothesis testing, the normal distribution is of utmost importance. So the distribution that is operating here is binomial distribution. There are two outcomes for every experiment, 1 or 0, that means head or tail. So binomial distribution can be approximated by normal distribution. We'll see how normal distribution is brought to play here. The normal approximation to binomial distribution happens this way. For any normal distribution, we need the mean and the standard deviation. The mean is given as n into p, that is 100 into p. P is 0.5, which is equal to 50. Okay, so the mean of the normal distribution is 50. So now, do you see the importance of null hypothesis? Okay, could you get the mean of the normal distribution without p? You do not get the mean of the normal distribution without p, and p is 0.5 because of null hypothesis. Okay, see how the brain has started moving after the null hypothesis has been set up. Okay, so the mean of the normal distribution is 100 into 0.5, which is 50, and the standard deviation is also needed for the normal distribution. So which is square root of n into p into 1 minus p. So this is from some results in probability. So this is equal to square root of 100 into 0.5 into 0.5, which is square root of 25, comes out to be 5. So the binomial distribution, which is operating under the coin clause, is now approximated by a normal distribution whose mean is 50 and the standard deviation is 5. So if we know the mean and the standard deviation of a normal distribution, we can always set up a standard normal variable, that is z. So z is equal to x minus 50 by 5, okay, where x is the number of heads. The number of heads we have obtained out of 100 is 70. So x minus 50 by 5 will be obtained by 70 minus 50 by 5. So the corresponding z value will be obtained. Okay, fine. So just remember the original question. We have got 70 heads out of 100. Can we say that the coin is unbiased? We have started with the hypothesis that the coin is unbiased, which means probability of head is 0.5. Actually, the probability of head will not be 0.5 because of the data. We are observing the methodology. So z equal to x minus 50 by 5. So for x equal to 70, which is the observation, Z equal to 70 minus 50 by 5, which is 20 by 5, which is equal to 4. So now if you look at the normal curve, the standard normal curve here, the standard normal curve is giving you uh, minus 1.96 to plus 1.96 as the 95% confidence interval. Okay. The probability of the area, the probability of Z being within minus 1.96 to plus 1.96 is 95%, 0.95. Okay. Now, the Z value which we have got is 4. Okay. So 4 goes beyond 1.96. It goes in this region, right? It goes in this region. It goes beyond 1.96. Okay. So then we say that since the Z value is outside the confidence interval, I cannot reject, I can reject the hypothesis. Okay, so that is the methodology. We are going to see why is it so. So the algorithm is very simple. We take the value of interest in the observation. Number of heads is the value of interest for us. Subtract the mean of the normal distribution divided by the standard deviation and see what is the value of Z. Now, where did 1.96 come from? We say that our confidence in our claim should be 95%. Okay. So the moment we decide that 95% is my confidence limit, confidence interval, then I am bound by these two values, minus 1.96 and plus 1.96. Okay, so 1.96 and plus 1.96 are called critical values, ZC. Okay, that's called ZC. Critical values. So if the Z value falls beyond critical value in the on the negative side or the positive side, then we say that the null hypothesis is rejected. Okay? So this is the methodology. But there is further depth to the discussion. What about 99% confidence interval? 99% confidence interval gives me the value minus 2.58 and plus 2.58. Z value is 4. For 99% confidence interval also, I'll have to reject the hypothesis. Okay, the hypothesis is rejected. The coin is not unbiased. And similarly, for the 68% confidence interval also, the hypothesis is rejected. In all these confidence intervals, the hypothesis is rejected. Okay, let us proceed and see what does it mean. So we have sort of established our intuition that the coin cannot be unbiased by this methodology. Okay, so let's progress further. So for x equal to 70, 4 is greater than 1.96, falls outside the 95% confidence interval. 4 is also greater than 2.58, and therefore the null hypothesis is rejected. So what is it we learn? We learn that there is a Z critical value the moment you decide on the confidence interval. Okay, so if I decide the confidence interval to be 95%, which is mostly the case, and you have probably seen this in lots of research papers, 5% significance level or 95% confidence interval. Okay, well, the both of them are actually the both of them actually mean the same thing. So then, if the Z value, the observed value, falls beyond the confidence interval, then we say that the null hypothesis should be rejected. So now we come to a more intuitive situation, which we introduced last time. So what you learned is if Z is greater than if Z is beyond Z critical, then reject is 0. Z critical is a function of confidence interval. Okay. So we should have, of course, done confidence, interval estimate. We'll do this immediately. So if the confidence interval is 95%, then C is equal to plus minus 1.950. So one thing we asked is that what is the probability of our observation? Okay, the probability of our observation is of very critical importance to us. The probability of our observation happens to be p to the power 70 into p to the power 30, or p to the power k into p to 1 minus p to the power n minus k, right? So that is the probability of the observation. So in this case, as you see on the screen, the probability of x is equal to 70, okay, given this observation is 0.5 to the power 70 into 0.5 to the power 30, given the observation. I'm not talking about all possible sequences where we have x equal to 70. Only one sequence has appeared in front of me, and the probability of that sequence is 0.5 to the power 70 into 0.5 to the power 30. So let's find out the probability of this observation by Z-score method. Now observe this technique which is used in probability very frequently. We know that for continuous distribution, the probability of any point is equal to 0. Okay, so that will not serve our purpose. So probability of x equal to 70 should be estimated from probability that x lies between 69.5 and 70.5. This is a very standard procedure which is used in probability all the time. Okay, when you use a continuous distribution and you want to find out the probability of a particular instance. So probability of x equal to 70 is equal to probability of x lying between 69.5 and 70.5. Therefore, which is equivalent to saying z is between 69.5 minus 50 by 5 and 70.5 minus 50 by 5. Is it okay? So z should lie between 3.9 and 4.1. So verify that this is all right. 69.5 minus 50 by 5 is 3.9. Okay. Now z is lying between 3.9 and 4.1. This must be equal to z 4.1 minus z 3.9. Why so? Why is it so? From the last class's discussion on z-score table.
Is 4.1 minus 3.9 will give the big.
Yeah, but why is z 4.1 minus z 3.9? No. What is z 4.1? Yeah. Okay, complete the story. The z 4.1 is the area under the standard normal curve from minus infinity to 4.1. And z 3.9 is according, right? So how much is this value? Let's see the z-score table. So how do we read the z-score table? Okay, z of alpha is obtained from going to an appropriate row and column. So z 3.9, how do I find out? Z 3.9. Is there any value 3.9 in the Z score table? It finishes at 3.4. Okay, and at 3.4, the value is almost 1 at 3.4, right? And what about 4.1? The value will be still closer to 1. So what do we find? We find that this probability is going to be extremely small. Okay, it is extremely small, and the probability of the observation under null hypothesis is called the p-value, a very important definition. So what definitions we have learned so far? The z-score, the confidence interval, and the p-value. So p-value, please note carefully. P-value is the probability of the data, the probability of the observation in front of me, if the null hypothesis is true. Okay, so if the null hypothesis is true, the probability of obtaining 70 heads is extremely, extremely small. But how small? How small? Okay, it's very small, but its absolute value is not important. What is important is whether it is smaller than the level of significance indicated by confidence interval. So this is another term introduced. Confidence interval automatically introduces another concept that is called level of significance. Okay, please pay attention to these concepts. These concepts are very basic, but at the same time, quite tricky also. Quite tricky. So level of significance is 1 minus confidence level. So if you have decided your confidence interval to be 95%, level of confidence to be 95%, I demand that value. Then the level of significance is 1 minus 0.95, which is 0.05. Okay, so if the p-value is less than the level of significance, the null hypothesis has to be rejected. Okay, so two conditions for rejecting null hypothesis, two equivalent conditions for rejecting null hypothesis. Make it greater than. The equivalent condition for rejecting is so this is not a class in probability. This is a class in AI. In particular, a particular branch of AI called NLP, which makes use of machine learning. Okay, so therefore, beyond this formula and the mathematics, our intuition has to be established. Okay? So this is more interesting. It says that if the probability of the observation, okay, under null hypothesis is below a low water mark, which is alpha, then we have to reject the null hypothesis. The probability has become so small, okay, that we have to reject the null hypothesis. How small? That smallness is to be quantified. The smallness is linked with the confidence interval. 95%, the allowable limit is 0.05. 99%, allowable limit is 0.01. Okay, so picture in your mind the fact that the probability of the observation has become very low. But observation cannot have low probability. Observation is awkward. So what is wrong? The null hypothesis is wrong. Okay, how wrong? There is a confidence level for this. That is the idea. Okay, so let's compute the p-values. We are not able to compute the p-value in this case when there are 70 heads out of 100 tosses. Okay, my z value has gone beyond the values specified in the z-score table. So I know that the value is going to be extremely small. It is surely going to be less than 0.05, 0.01 also. Okay. Let's say x equal to 60. Now I observe a different value, number of heads, x equal to 60. This should boost my confidence or increase my confidence in the coin being unbiased. Okay, the probability that the coin is unbiased should increase now. Is it so? Let's verify through the method of hypothesis testing. If x equal to 60, then z value is 60 minus 50 by 5, which is 2. I can reject it for 95% confidence interval, but not for 99%. So 2 is beyond 1.96, but 2 is not beyond 2.58. So if my confidence interval is 99%, I cannot reject. 95% confidence interval, I can reject. Why? What is the intuition? Let us see the intuition. And 55, it's equal to 55. The inclination to think that the coin is unbiased should still get more support. Okay, let us see. So x equal to 55, z is 55 minus 50 by 5, which is equal to 1. I cannot reject under 95% confidence interval. Now the z value has come inside the confidence interval, 1.96. Okay. And it is surely within 2.58. So under 99% also, I cannot reject. Fine. Now let us see. P-value. The p-value for x equal to 60. Actual value of the probability of the observation is 0.5 to the power 60 into 0.5 to the power 40. Let's look at what z-score method gives me. Probability of x equal to 60 is probability that x is between 59.5 and 60. Oh, 60, right? Between 59.5 and 60.5, it should be. Sorry, 60.5. 60.5. So this will be 60.5 minus 50 by 5, which is equal to how much? 2.1. And this will is okay. 1. So I'll make that correction. So I'm interested in Z 2.3 minus Z 1.9. Z 2.3 is 0.9893. What is the value of Z 2.1? Z 2.1, how much does it? 0.1. Zero point. And Z 1.9. Always get 8. Determination. But of course, it is, I'll make that correction. 97, which is equal to how much? 0.01. 0.1. 0.8. So I'll take that approximately. Okay. So if you have got the data as number of heads being 60, then the p-value, okay, the probability of the observation is 0.011. And the level of significance, if 95% confidence interval, then the level of significance is 0.05. So this value 0.011 is less than 0.05. Therefore, I reject the hypothesis if my confidence interval is 95%. But if my confidence interval is 99%, then 0.01 is the level of significance. And the p-value is more than 0.01. I cannot reject the null hypothesis. Okay. So for 99% confidence interval, I cannot reject. 95% confidence interval, I reject. And then you will come and ask if I have to decide whether to reject or accept the null hypothesis. Should I reject or should I not? 99% confidence interval is telling me there is no ground to reject. 95% confidence interval is telling me you should reject. The data is not consistent with the null hypothesis. So do you see there is a triangle? There is a triangle emerging. And let's check for 55% also. For 55, the confidence in the coin being unbiased should increase. So Px equal to 55 is this by z-score method. Px equal to 55 is 54.5 and 55.5. So Z has to be between 0.9 and 1.1, which is Z 1.1 minus Z 0.9, 0.8643 minus 8159, which is 0.04. Okay, which is 0.04. Right. Now, so we see triangle is this has to be different. So what is emerging is a three-way interaction between the data, the observation, the observer's hypothesis in the mind, and the observer's requirement for confidence. These two things are observer dependent. The observer decides. The observer decides in unhypothetically. The observer decides what confidence level he or she wants. And out there is the reality, which cannot be tampered. It's experimentally. Okay. So do you see some quantum information gradually emerging? Those of you who are thinking of doing some project in quantum NLP and so on. The whole discussion is so observer dependent. Where is the objectivity? The observer decides, makes a null hypothesis. The observer decides the confidence interval for the level of significance and looks at the data. Okay, so the whole hypothesis testing mechanism is a function of the observer's predisposition, the observer's confidence, and the data. So have we forgotten NLP? Okay, you'll ask, what has happened to NLP? The class in where is NLP gone? Okay, the point is that if everything that we hear, that we produce, everything that we try to make meaning out of, has an element of subjectivity. The sentiment analysis definition, the bias definition that you saw, has inbuilt in it a component which is the speaker's contribution, the hearer's contribution, the listener's contribution, and so on. Okay, so there will be a quiz on 24th. There will be a quiz on 24th. How are you receiving this information? Some of you are extremely delighted, right? There will be a quiz. Oh, wow. 24th, there is a quiz. I don't know. Are you? And some of you are probably anxious. Okay, I'm going. Huh? No. So one statement causing different sentiment, different feelings in everybody's mind. Why? Okay, so let's remember that AI has very intimate connection with probability. And hypothesis testing, where we try to take a leap of generalization, is dependent on these three entities: the data, the null hypothesis, the confidence interval that we have. The p-value is more intuitive. Confidence interval is more mechanistic, easy to implement as an algorithm, which is why you have packages for hypothesis testing. But p-value directly shines the light on the situation. The probability of the observation under the null hypothesis has fallen below the level of significance. But the data cannot have low probability. I have to reject the null hypothesis. Okay, but the intriguing thing is that when you change the level of confidence, then the decision to reject or accept also changes. What is the intuition behind that? That we should understand. Okay, especially since the discussions are on NLP, we should be clear on this. Yes. Okay, now I think all of you have now started working on course projects. So there is considerable weightage on the course project with respect to your grade. So do please, start working if you have not started working already on your course project. And there are some interesting projects which are very relevant in today's world. So one of the groups I suggested they work on finding out if the text generated is written by a human being or by ChatGPT. So this is not a novel problem at all. I believe MIT softwares which can give this decision of whether the text is written by ChatGPT or by human being with reasonable confidence. Again, reasonable confidence. Okay, some probability value. So with high probability, they can detect if the text is by ChatGPT or by human being. So this is an interesting project, and I think, and one of the groups is this. I think you are thinking whether to do this or not, right? Right? Yeah. So there was a newspaper report that some of these tasks are being done by looking at a few keywords. So apparently, the word. So I'll show you in the next class which are the giveaway keywords for ChatGPT. So it has been seen that after ChatGPT arrived, the ChatGPT written text has some of the words which are extremely frequent. Delve into has become very frequent suddenly. Okay, after ChatGPT arrived, the preponderance of this word delve into has suddenly increased a lot. So either ChatGPT written text or ChatGPT inspired text is causing this. Delve into has become a very frequent word. Then similarly, there are some phrases to in all practical purposes. Apparently, is also a high frequency phrase. So before ChatGPT, these phrases and keywords were not so frequent. Suddenly, their frequency increased a lot. So probably you have to make use of these signals to decide if the text is written by ChatGPT or not. Okay, another thing I'd like to read to you. I'll create slides for that also. So our ancient Indian approach to knowledge has said that there are 6 channels of acquiring knowledge. So the most frequent is the pratyaksha. Pratyaksha is the direct sensory experience. Okay, and then there is anuman, which is inferencing. Okay. So in the era of large language model and generative AI, researchers are finding correspondence between these 6 or 7 methods of acquiring knowledge and LLM-based operations. Okay, a robot, for example, has these 6, 7 channels of acquiring knowledge: Pratyaksha, Anuman, Upaman, and so on. So I'd like to present it to the class because we see that this ancient knowledge has a lot of relevance to LLM generative AI based Gen AI based AI. Okay, so on Monday I'd like to discuss this. So now, the fact that the data is of supreme importance and you will have to reject whatever notions or hypotheses you have in mind, that we discuss very nicely using this the puzzle from logic, okay, where we say that there are these facts of ABC belonging to a class, belonging to a club, and every member in the club is either a mountain climber or skier. A likes whatever B dislikes and dislikes whatever B likes. A likes rain and snow. No mountain climber likes rain. Every skier likes snow. Is there a member who is a mountain climber and not a skier? So this is a puzzle, very popular kind of puzzle in competitive exams, and we found out that the answer is B. And the proof was by contradiction. So hypothesis testing is also proof by contradiction. You assume a null hypothesis and look at the data. The data tells you if the hypothesis can be accepted or rejected. Okay? So this is the method. And this method is at least 2000 years old. Okay. See the consequence of your assumption with respect to the observation that you have made. Observation is good. The assumption or hypothesis is vulnerable, can be rejected or it cannot be rejected. So this is at least 2000 years old. The hypothesis testing is about 500 to 600 years old, which was born with the probability. So what is hypothesis testing? It is proof by contradiction along with probabilistic score. That is the new thing. Okay, it is also proof by contradiction, but the contradiction is not 1-0. The contradiction is probabilistic. Okay, so that decision is again is a gray event. So let's go to the foundations of hypothesis testing. We have jumped again a bit. The main technique is interval estimate. Okay, so sample mean and population mean. If x1, x2, x3 up to xn is a sample from normal distribution, having unknown mean mu and known variance sigma squared, then the maximum likelihood point estimated for mu is x bar, which is sigma xi by n. Okay, so we know that the best possible estimate for the population mean is the average of this is the mean of the sample, okay, which is computed this way. So it can be proven that this is the best possible estimate of the population mean. Now, if we take different samples from a distribution, first a normal distribution, and you will get different mean values from each of these samples. And let's say the sample size is same everywhere. This is n. Then we know that x bar is normally distributed. Okay, the mean of the sample itself is normally distributed. Why is it normally distributed? Because the sample is varying and it is being taken from a normal distribution. So the distributed will mean mu and known standard deviation sigma by root f. So the following is a standard normal distribution: x bar minus mu by sigma by root f. So that's very nice, right? You can create a standard normal distribution from the means of the samples, which is x bar minus mu divided by sigma by root n. Okay. Then now comes the important result which we use and which is very interesting. So probability of x bar minus mu divided by sigma by root n. So x bar minus mu divided by sigma by root n lying between -1 to 1.96, 1.96 to 1.96 is 0.95. It has to be so. Okay, because of the property of standard normal distribution. So now with some algebraic manipulation, we are able to come to a conclusion that if the sample mean is x bar, okay, then the population mean has to be within this limit. X bar minus 1.96 sigma by root n and x bar plus 1.96 sigma by root n. The population mean has to be within this interval, which is so interesting. Okay. If you get the sample mean, the sample size, and the standard deviation, the behavior of the mean is restrained now. So population mean is restrained. Population mean cannot be anything arbitrary. It has to follow this constraint. It has to be between x bar minus 1.96 sigma by root n and x bar plus 1.96 sigma by root n. Has to be. So we apply this idea. Suppose a machine part manufacturer has made parts with the dimensions as given below. 9 pieces of the machine part. Dimensions are respectively 5, 8.5, 12, 15, 7, 9, 7.5, 6.5, and 10.5. So suppose somehow it is known that if the parts could be measured in the whole population sample by sample, the variance of the measurement of the dimension would be 4. Suppose it is known somehow. Okay. Let us see. The mean of the sample is 81 by 9, which is 9. Then from the result that you have seen already, the 95% confidence interval for mu is 7.6 and 10.31. The population mean has to be between 7.6 and 10.31 as per the sample, because of the sample. Okay. So therefore, based on the observation of 9 samples and knowledge obtained somehow that the variance is 4, we reach the 95% confidence interval 7.69 and 10.31. So that means the manufacturer part, the dimension has to lie between 7.69 and 10.31 with probability 9.95. Okay, and with probability 0.99, these values will be different. If you want 99% confidence, will the values be smaller or larger? Will the gap between the two values increase or decrease? For 99% confidence interval, minus 1.96 will become minus 2.58. And plus 1.96 will become plus 2.58. So then what can we say? The gap will decrease or increase? Increase. The gap between the lower limit and the upper limit will increase for 99% confidence interval. Intuitively, what does it mean? Why is this behavior? Sample size is same, standard deviation is same, sample mean is same. Just because of 99% confidence interval, the gap has increased. Why so? Yeah, we're allowing more freedom. Okay, the span is now large, minus 2.58 to plus 2.58. So the value falling within this range has higher probability. Okay. So if the manufacturer now says that I can ensure a part dimension of 15, we cannot trust. Cannot trust based on the 95% confidence interval. If the maker says I assure a dimension of 10, we can trust. We are operating with a confidence level of 95%. Okay. So sometimes there is a need for upper confidence interval and lower confidence interval. So so we'll come to that. Now there is this type 1 and type 2 error. Type 1 error is incorrectly reject H0 null hypothesis when it should have been accepted, and H0 is actually true in the population. Type 2 error is incorrectly accept H0 when it should have been rejected. H0 is actually false in the population. So this contingency table is useful here. the type 1 and type 2 error are always with respect to null hypothesis. Okay, when we say accept or reject the hypothesis, it is always with respect to H0, never with respect to alternative hypothesis, HA or H1. Okay, that is the notation. So as per the data, we have accept and reject options. Actually, true and false. Then as per the data, accept. And actually also the hypothesis is true, then there is no error. So the first quadrant, there is no error. If the hypothesis is actually true, but we reject as per the data, then we are making type 1 error. The second quadrant. If the hypothesis is false and we are accepting it, the fourth quadrant, then we are committing what is called the type 2 error. And the third quadrant also is all the diagonal quadrants are no error quadrants. Okay. So this diagram is very useful to us, which is the confidence intervals and the Z critical values with respect to that. Minus 2.58 plus 2.58, minus 1.96 plus 1.96, and minus 1 and plus 1. So this example we looked at last time. We do it again. A factory has a machine that the factory claims dispenses 80 ml of the fluid in the bottle. This needs to be tested. A sample of 40 bottles is taken. The average amount of the fluid is 78 ml with standard deviation 2.5. Okay, verify the factory's claim. The factory is claiming 80 ml. So the claim population mean is 80. The sample size is 40. The sample mean is 78. Sample standard deviation is 2.5. So we first take the null hypothesis that the manufacturer's claim is correct. Okay. We establish the null hypothesis this way, which we would like to reject. And alternative hypothesis, therefore, is mu is not equal to 80. So if we do the two-tailed analysis, we do not want the fluid to fall below 80 or above 80. Then we have the equality test and the two-sided test. So Z critical, therefore, is plus minus 1.96 because the 95% confidence interval has been decided on. So from the observation, we have the sample mean as 78. The population mean is assumed to be 80. You could not have written 80 there if you did not have the null hypothesis. Okay, everything starts like a train after the null hypothesis. Now 2.5 is the standard deviation. Sample size is 40. So Z observation is coming out to be minus 5 approximately. So this is falling in the rejection region. If you compute the p value, you will see that this p value is also below the level of significance, 5%. So we reject the null hypothesis. The claim that the machine fills bottles with 80 ml fluid is rejected based on the evidence. Suppose we work with 99% confidence interval. Then the Z critical will become plus and minus 2.58. Minus 5 is again less than minus 2.58. So for 99% confidence interval also, the hypothesis is rejected. The manufacturer is not giving 80 ml on an average in the bottles. What about 90% confidence interval? Then the critical value of Z is plus minus 1.28. So again, minus 5 is below minus 1.28. For 90% confidence interval also, the hypothesis is rejected. Okay, so whatever be the confidence interval, the hypothesis is always rejected. That means the p value, the probability of the observation, is below the significance level in all three cases. So that is what is typically done. Now we have to reject the claim of the manufacturer. He is most likely with very high probability not giving 80 ml of fluid in all the water.